Okay, let me continue to express a technique for the accelerating the convergence of a sequence. The technique is called Aitkens delta squared method. Let me introduce a sequence Pn, n from 0 to infinity, as a linearly convergent sequence. This means that Pn converges to P, for example, linearly. Also, let the sign of the difference between Pn and Pn plus 1 and Pn plus 2 and P and so on are the same. It means all the signs are positive or negative. And consider this almost equality. In fact, Pn plus 2 minus P over Pn plus 1 minus P is almost equal Pn plus 1 minus P over Pn minus P, and this is almost equal to lambda, that is the asymptotic limit. Okay? If we multiply this item in this one and this one in this one, we will get Pn plus 1 minus P squared is almost equal to Pn plus 2 minus P times Pn minus P. Okay? And if we expand the left hand side and the right hand side, we will get Pn plus 1 squared minus 2 Pn plus 1 P plus P squared is almost equal Pn plus 2 times Pn minus Pn plus 2 plus Pn times P plus P squared. We cancel P2 from two sides and we try to find P from this inequality, equality. Okay, so let me show you something here. Here you can consider, you can keep Pn plus P squared plus 1 and Pn plus 2 times Pn in the left hand side. In fact, it will be Pn plus 1 squared minus Pn plus 2 times Pn. This is almost equal, and move this one in the right hand side, okay, to get Pn plus 2 plus Pn plus 2 Pn plus 1 times P. Okay, from this we get P is equal to the left hand side as a nominator, Pn plus 1 squared minus Pn plus 2 times Pn over, and here we will get Pn plus 2 plus 2Pn plus 1 plus Pn. I think I have some mistake here, and it should be, yeah, here it should be minus, and this is positive, I guess. Let me do it in another way, maybe a better way, I mean. Let me remove all of this. Okay. And I start like this here. Yeah, Pn plus 2 plus Pn times P minus 2pn plus 1 times p is equal to pn plus 2 times p minus pn plus 1 squared. Okay, here we can factor p and we will get pn plus 2 plus pn minus 2pn plus 1 is equal to pn plus 2 times p. It should be pn minus pn plus 1 squared, and from here we can get p is equal to pn plus 2 times pn minus pn plus 1 squared over pn plus 2 minus 2pn plus 1 plus pn. In fact, this is almost equal. If we want to say the correct sign, it should be almost equal. Now, in this part, now you add and subtract two terms, pn squared and 2pn plus 1 in the denominator. So we will get p is almost equal pn plus 2. It's written here, in fact. Look at here. Let me maximize it and show you. Now, add and subtract 2pn pn plus 1 and pn squared in the denominator. We will get pn plus 2 minus 2pn plus 1 plus pn squared minus pn plus 1 squared plus 2pn plus 1 minus pn squared. Okay? In these three first terms, you factor pn. It remains pn plus 2 minus 2pn plus 1 plus pn. And here factor a minus 1, okay, a minus sign, in fact, here. You will get pn plus 1 squared minus 2pn plus 1 plus pn squared. If you, in fact, divide both terms over on the denominator, you will get pn from the first one, and here you will use the first, in fact, from this one. A plus b squared equal to a2 minus 2ab plus b squared. In fact, it should be minus. So we will get pn plus 1 minus pn squared over this one. Okay? This will called the delta squared Aitkens method. Okay? So if you construct a new sequence called pn hat for n from 0 to infinity, you can define pn hat to this form. This sequence converges to p very faster than the original sequence pn n equal to 0 to infinity. Okay, this is the delta squared, Aitkens delta squared. But why we say delta squared? What's delta? In fact, for the illustration of the delta, we should consider an operator we call the forward difference. What's the forward difference for a term of sequence? We define delta pn to form pn plus 1 minus pn. Okay? And we define delta k pn equal to delta times delta k n k minus 1 pn for k greater than or equal to. Now, if you consider, for example, delta squared Pn, it will be delta Pn. Look at here, delta squared Pn is equal to delta Pn. And delta Pn is Pn plus 1 minus Pn. We defined it here, we put here. And delta, it should be equal to delta Pn plus 1 minus delta Pn. And delta Pn plus 1 is Pn plus 1 minus Pn plus Pn plus 2 minus Pn plus 1 minus Pn plus 1 minus Pn. If we apply the minus in the parentheses, we will get delta squared Pn is Pn plus 2 minus 2 Pn plus 1 plus Pn, that it is exactly the denominator of this one. In fact, this is exactly delta squared Pn. Okay, and here we will have delta Pn squared. Finally, we will get a new form for the sequence. Pn hat is equal to Pn minus delta Pn squared over delta squared Pn for n greater than or equal 0. Okay, for this reason, we call this method as the Aitkens delta squared method. If we apply this sequence to finding the root of equation, nonlinear equation, we will have a very faster convergence. For example, for cosine of p equal to 0, if we use Pn, we will have this form of convergence, and if we use Pn hat, we will find this form of convergence. You can see that the convergence for Pn hat is much faster than Pn. Okay, now let me show you and compare the rate of convergence, in fact the speed of convergence in some different methods. As an example, suppose that we want to find the roots of the equation x cubed minus x minus 1 equal to 0, both with Newton method and with Aitkens delta squared method. Okay, for Newton method we have to define y equal to x cubed minus x minus 1 and yp as 3x squared minus 1, and we solve the equation with, for example, this accuracy. Okay, and with starting point x1 equal to half. Okay, if we solve the problem, you will get 20 iterations to finding the the root. Okay, now let me do exactly the same equation with the same accuracy. Let me change the accuracy to 0.50 and 1, and I define y as x plus 1, okay, to power of 1 over 3. Now let me try the equation. You will get just 6 iteration to the same root, in fact. So you can see that the rate, the speed of the convergence is much faster than the Newton method. So Aitkens delta square can be a very good choice for solving the problem and solving the and finding the roots of a nonlinear equation. Let me show you another example, but before that let me try to solve in fact, the equation x cube, let me show you, x cube minus x minus 1 equal to 0, both with fixed point and with delta square, delta Aitkens delta squared. We know that in both delta squared and fixed point, x should be x plus 1 to power of 1 over 3. In fact, something you can see exactly here, right? In both delta squared and fixed point, this part is same. Okay. Now let me run this one. You can find the solution in 10 iterations, and if you try the same in delta squared Aiken, you can find the solution in just 6 iterations. So this technique is in fact faster than linear convergence. Now let me show you another example. For the next example, suppose that we want to solve this equation. Let me write the equation here for you. The equation is in fact 3x e to power of x minus 1 equal to 0. So we should get f of x equal to 3x e to power of x minus 1, and in both fixed point and delta squared Aitken, we should consider x as equal to 1 over 3e to power of x. Okay, now let me show you the result of the implementation. For example, first one for fixed point, we have to consider y equal to 1 over 3 exponential of x, and for delta squared Aitken the same. Okay, now first let me try fixed point. We get the solution in 12 iteration, and then let me try the delta squared Aitken. We will get the solution in just 9 iterations, 3 iterations less than the fixed point. So if the fixed point method is linearly in fact convergent, the delta square Aitken is converged to the root of the equation with more than 1 in fact rate of convergence. This is some example of the convergence and the delta squared Aitken. In the next lecture, we will compute the roots of the polynomial with a new technique we call the Horner method for computing the in fact the values of f of x and f prime of x. Please subscribe my channel and introduce my channel to your friends. Thank you.